Claudia's got the drive tube inserted into the ground, and I'm hammering away here.
We are actually doing a dress rehearsal for the moon. Like, we're really going to the moon, and we're practicing that right now.
We have this massive legacy of how to do this and how to do this well. This is our Apollo. We're all so excited to be part of this.
We're really doing this, and I'm so excited. When I came to NASA, one of the things I wanted to work on was a mission to the moon, and we're there now. We're training crew members, we're building hardware, we're starting to practice the operations, we're building new relationships and collaborations to be able to send humans to the surface of the moon to collect new samples, understand new geology that'll help us answer some questions about the Earth-Moon system. During Apollo, we sent 6 missions, 12 astronauts to the near side of the moon. It's really a very small part of the moon. So we know that we haven't sampled the whole of the moon. We know that other parts of the moon are going to look different. They're going to have different rock types.
So I'm a geologist. I love to think about all the science we've accomplished with lunar exploration, but we went to a pretty geographically and geologically constrained part of the moon with the Apollo missions. On Artemis, we'll visit the lunar South Pole, we'll make observations from orbit, and we have a whole new set of science questions that we hope that Artemis astronauts will help us answer. We hope to learn about the evolution of the moon, but actually a lot of the objectives that those astronauts are going to be doing will tell us about the evolution of our own planet and the entire solar system.
We learned from the Apollo rocks so much about the Earth-Moon system, about ourselves, but Apollo raised so many more questions. And so now, going back with Artemis, we're going to go to an area in the South Polar region that is way more representative. So when we collect samples there and bring them back, we can test all these hypotheses that we came up with when we looked at the Apollo samples. And now going back and picking up these rocks, we'll be able to answer some of those questions.
The astronauts on the surface of the moon, they're proxies for the scientists. They can observe and describe in a way that a remote sensing instrument or a rover cannot. And so it's more than just collecting samples, it's collecting the context for the samples, being able to put all those pieces of information together to be able to tell the story. So we've been working for some time now, putting together a plan for training astronauts in geology and in combined geology and surface operations. We want to make sure that the crew members have the geological language, they understand the terms, they understand how that stuff fits together. So we have classroom lessons in geology, basic lunar science. That will get the astronauts ready for taking them out into the field.
You're going to see a feature that's just like this, exactly like this. First you observe, and then you can start making interpretations. You guys are scientists at this point.
And we plan several different field trips in different locations that have lunar relevance, where they can start to put that classroom knowledge to work.
This week we're here in beautiful Iceland, training the Artemis II crew and planning for our future Artemis missions out here, and then also doing a simulation with tools and techniques and operational concepts.
Iceland is a really wonderful place. It's a great place of interest for geologists, but it's also a wonderful analog for the moon and Mars.
The good stuff is at the outcrop. And so if you have an outcrop, that's the preferred sampling because, again, context is really important.
Artemis II won't be landing on the moon. We recognize that, but they're going to be observing the moon, and they still need to be able to observe, describe, document the geological features that they're going to be seeing. They're also doing some ground truthing for us for future Artemis crews. They're providing us real-time feedback about the relevance of the training.
Pretty cool, right? Inside, outside looks good for everyone.
There's really transformational science that we can learn by getting boots back on the moon, getting samples back, and being able to do field geology with trained astronauts on the surface, making observations that only they can make from that perspective.
All right, great. So here what we're trying to do is get a chip sample using our hammer and chisel, and then we'll use the tongs to pick up that sample and put it into a sample bag.
I've had a fantastic opportunity to participate in a number of different simulations out in the field, also underwater simulations in the pressurized suit. The water environment definitely gives you the 1/6 gravity offload feeling so that you can then maneuver a little bit more like space-like. The field environment gives us the large scope and the science fidelity that we're looking for. If we can use the geology out here in the field environment in a much better way than we can simulate in the water environment. So both have a key role in understanding the mobility in the water environment, but then the science fidelity and scale that we get out here in the field.
Okay, ground EV2 here. I've done my scoop sample as directed. It's in sample bag 3475. I have about the bag halfway full. The material is dark tan. It's nice and fine grained.
Okay, we copy bag number 3475.
So the Jet 5 test, it's a multi-parameter test, but it includes astronauts in the field with mock spacesuits and mock tools. They're in a planetary relevant location, and it includes a science team back here in Houston. What we're trying to do is understand, how do scientists work together as a team? How do we communicate with the broader flight control team? How do they communicate with us? And how do we as collectively communicate with astronauts on the surface of the moon?
It's just been really cool to feel how real it is. So as a crew member, I need to be thinking about things like my spacesuit. You know, is my spacesuit working correctly? How is the pressure holding? Do I have all the consumables and oxygen that I need? How are my tools functioning? And then what kind of science am I doing? So I'm thinking about all of those things in my head as I'm doing these lunar traverses. And then we're talking to the real team of scientists. So when we go up to an outcrop and we're making observations about it, and the science team has questions about that, we're talking to those real scientists that are also going to be doing this on the surface of the moon. So it's a really high fidelity practice for all of these different areas that we're trying to integrate.
But we're also testing what kind of software tools do we need, right? How do we best track the sample mass? How can the science team understand that when the flight control team says no, that we're going to be okay with this? So these are all these different things we're trying to figure out and learn. The fun part about this test is it's a test. We can try different things. We can learn the lessons that we didn't even realize we still needed to learn, so that we can all work as one big team.
We have now 1.15 kilograms extra for tomorrow. We used to have 2.15, but with that secret pink spinel rock, we're now down to 1.15 kilograms that we can use tomorrow. That is the bonus for tomorrow, yeah, in addition to whatever else was planned.
The NASA Johnson Space Center here in Houston has this like massive history and a legacy of working with the Apollo samples when they brought back. And so from the Apollo samples, we really learned how to not only store and preserve them best, but also how to think about materials that come in contact with them. And so all of that will be applied to Artemis. And so the Artemis 3 and Artemis 4 mission samples will be stored in the Apollo lab. There's space there. It's a state-of-the-art lab. It's super good at protecting the samples and preserving the samples. We have updated our procedures of how to do this so we can include new technologies. When Apollo came back, they weighed the samples, they looked at them, they took pictures, right? Now cameras are so much more evolved, right? We can take amazing images, but you now can build a 3D model of it. And so that's what we're gonna do with Artemis. We're gonna CT scan them so that we can look on the inside without touching the samples and making sure we can do that in a nitrogen atmosphere so that they're never ever exposed to Earth atmosphere. And then we're gonna create a catalog for the world to see. And then any scientist can request samples and do all the amazing science that they can do on these samples. I feel just so lucky and grateful that I get to do this and I get to see the samples and like enable science for other people to do, right? I'm just helping other scientists to do the best possible science that they can potentially do. So exciting.
We need to celebrate this moment in human history because Artemis is more than a mission to the moon and back. It is the next step on the journey that gets humanity to Mars.
We want to study the moon because the moon holds some of the secrets to understanding the Earth-Moon evolution, the early history of the Earth, the early history of the solar system, and 4.5 billion years of history that we really care about.
I can't wait for the day that we get to see this and be part of it, right? This is our Apollo. Like, none of us, this new generation of a lot of women and early career people, like, we're part of this group of people. We're all so excited to be part of this.
Not only am I just so excited and passionate about what Artemis missions will do for science and what our crew members will be able to do for us as a geologic community, but the group of people that we're working with is truly spectacular. So I can't tell you how fortunate I feel and how passionate this entire group of people is about the mission in front of us, which is to send Artemis astronauts to the moon, bring them back safely, and accomplish a whole wonderful bunch of science objectives while we're at it.